Hello, I'm Nuno Carvalho, and today I'll be going over the solutions and answer explanations to the 2009 AP Physics C Electricity and Magnetism multiple choice exam. I have made videos on the 2004 and 1993 exams as well, and so you can check out those videos. And I plan to do one for the 2012 exam as well before May 3rd when the exam actually happens. Please enjoy the video and leave a like and subscribe if you want to see more. Starting with number one here, we're told that a point charge is initially at rest close to a bar magnet that is also at rest, and then we're asked about what will happen to that charge. Well, all of these answer choices here are describing some type of force, and we'd have to imagine here the force is going to be magnetic, given that it's next to a magnet. But keep in mind from your formula sheet that this is the equation for a magnetic force. Unfortunately, though, if the point charge is initially at rest, then that means that the velocity is zero, which means that the magnetic force will also be zero, and so none of the answer choices A through D are going to be correct. E is correct. There is no magnetic force being experienced by the charge. Number two, we're given a circuit here with a bunch of resistors, and we're asked about the current that goes through them, and we're asked to rank them from least to greatest magnitude. Well, what's going to be useful here is going to be knowing Kirchhoff's rule, which is to say that if we have a current going in this direction and then it splits off into two ends, then the volt or the currents of those two ends must add up to where it began, like so. So that is to say that if we have current I3 here going along here and then it passes through here and it splits off into two, well, by definition, these cannot be bigger than I3. Okay, so we already know that I3 is going to be bigger than I4 and I2. Okay, and so then we're left to think about this portion here, and because there are two resistors in parallel, then that means that they have the same voltage, okay? Which means we can just sort of look at their resistances here to figure out what the relative current would be. And so given that I is given by V over R, where keep in mind this here is staying constant, but for this one up here, we're increasing the resistance, which means we'd be decreasing the current, which is to say that from here, I4 will be less than I2 because the resistance again is greater. So putting all this together means that I3 is the greatest, followed by I2, followed by I4, and so the least is I4, greatest is I3. The answer choice that is correct is A. Number three, we're asked which of the following is a possible unit for an electric field, and if you know the answer, this is very quick. If you don't know it, well, you just need to look at the formula sheet, and you'll see that there are two formulas here that were given for an electric field. One of them is going to look like this, and the other one is going to also look like this here. And we can actually just use this to figure out which answer choice is going to be. This is often simplified to be voltage divided by distance, if you are in a constant electric field, which is to say that the units on this would be volts over meter. However, that's not something given here. We are given volt times meter, but not volts divided by meters. Okay, so let's think about this one instead. Have here a force, which is going to be in newtons, over a charge, which is going to be in coulombs, which is newtons per coulomb. And so the answer choice here is E. None of the other ones actually work out to be a proper unit of the electric field. Number four is a perhaps unusual question for an AP Physics exam, but we're told that an EMF is induced by a changing magnetic flux in the operation of all the following except. Then we're given here these 5 machines, and you might be thinking, how am I supposed to know all these things? Well, maybe you don't have to. From these, I can say that you should probably know these last two at least, an inductor and a mass spectrometer. And so let's just think about those two. An inductor, that's of course what you find in circuits, and it's a whole unit in AP Physics. And what you should remember is that basically the coiling here does create a magnetic field, and it does create an EMF that will oppose the change in current. And so D is definitely not the answer because it is something that uses a changing magnetic flux to induce an EMF. And so then we're left with a mass spectrometer. And that's the one where you have sort of a charge go through a field that has, a magnetic field that is. And then you sort of see the path of this charged particle. However, in none of that do you ever change the magnetic flux or induce an EMF. And if you think about it, you probably learned this before you learned about inducing EMFs. So I can safely say that E is going to be the correct choice. But if you really wanted to go into it, A, B, and C are going to be all machines that do induce an EMF. Number five, we're told that a solid conducting sphere carries a charge of plus Q. And we're asked which of the following is true of the electric field and the electric potential V inside of the sphere. Okay, this can be a very quick question if you know the words that you're looking for here. Conducting, that's the same thing as saying it's like a metal sphere, and something you need to memorize is that the electric field inside of a conductor is always zero. Okay, it's always zero, so we can eliminate C and D. Okay, what about the voltage though? Well, if we have here a conducting sphere, it will look something like this, and it's going to have its charge on the outside like this. Um, and you can imagine that this will create an electric field like this. So if you're thinking about the potential, well, there are two ways to think about it. You can either think about potential as the integral of E dx, and you can imagine as you're going from infinity here out to closer to the center right there to the inside of the sphere, that's definitely going to take some voltage, and so the voltage will not be zero. Another way to think about it is this whole sphere can be approximated by the formula that's in your formula sheet, which is like so. And so either way, this would show that there is not uh, there's definitely a voltage there that's not equal to zero. So the answer choice here that's correct is going to be B. Number 6, we're told that a capacitor with circular parallel plates of radius r that are separated by distance d has a capacitance of C. What would be the capacitance if the plates had a radius 2r and were separated by a distance of d divided by 2? Okay, so the formula here that's going to be useful is, once again, in your formula sheet, and it's this right here. This gives you the capacitance of a capacitor given its physical properties, more specifically the dielectric constant and also the area and the distance between the two plates. This is all we need, right? Only thing to know is that, area of two circular plates is going to be given by pi r squared. So we can say that our formula is going to now look like this. And so this is, let's just imagine this is the first capacitance. How does the second capacitance compare? Well, we are going to be doubling the radius, which means we actually have to multiply the top by 4, right? Because we have 2r and we square it. So we're left with this. And then the distance, we're halving it. So like that, which really is to say that we're actually going to multiply the top by 8. And so that means that C2 is going to equal to 8 times C1. And so the correct answer is E. Number 7, we're given a network of 3 resistors that are connected to a 20-volt battery, as shown, and we're asked about the equivalent resistance of the network. Okay, this is a very simple problem. It's one of the problems that people got the most right on the exam. First, you just need to add these two, which are in series, which means that the equivalent resistance is just adding both of them like so. And so that means that that one is going to be just 8K ohms like that. And then you have two that are going to be in parallel. And so keep in mind, we're thinking now about this 8K one and also this 8K one. And since they aren't parallel, we think about this new formula here, which once again is going to be given in your formula sheet. And once you plug those values in, you'll get that the equivalent resistance here is going to be 4K ohms. And so the correct answer is A. Number 8 is still dealing with the same circuit from before, and it's a slight step up in difficulty, but not too much. It's asking about the potential difference between points X and point Y. Well, what I would do for this question is realize if the voltage difference here is 20, then the voltage difference from here to here is 20, and so from here to here, it's also going to be 20. Okay, and then I know that voltage is basically going to have to do with the resistance that is in between here. And what I'll notice is that this is symmetric, right? Going from here to here is symmetric from going from here to here. And so if that's symmetric, and by that I'm specifically pointing out the resistances, then I can just quickly guess, and it would be correct if I actually did the problem, that there will be 10 volts going from halfway between this path right here. And so the correct answer is C. Number 9, we're told that the single circular wire loop of radius r shown above carries a current I that produces a magnetic field B at the center of the loop. If the current remains constant while the loop is enlarged to a radius of 2r, what happens to the magnetic field in the center? Well, unless you have it memorized, this is actually going to require a quick use of the Biot-Savart law, and if you don't remember what that was, this is in your answer sheet, or formula sheet, I should say, and it goes like this. All right, so very long formula, but it's actually not going to be too difficult here. So what we need to think about is that the full magnetic field of the entire loop is going to be given by the integral, where basically we're just taking a tiny segment of this loop here and thinking about what the magnetic field it is that it produces. So we can pull out all these constants here, like that, like that. The current is going to stay the same. We know that the radius is always going to be, well, the distance from the loop to the point is always going to be r. So we have r squared here. And then this here will just simplify to be dl because we're always going to be perpendicular to the point with how we're doing this. Uh, and what we need to know is that the integral of dl is just going to be 2 pi r, which is the circumference here of the loop or of the circle. So we have something that looks like this, which is to say that overall the B field or the magnetic field is going to look like this. And so all you need to think about is that if I was to double the radius, I'd basically be turning this formula to look like this, which is to say that we're basically making the field half as big. And so the correct answer here is going to be A. Number 10, we're told that a capacitor charged to a potential difference V stores an amount of energy U. If the potential energy is doubled, what is the new stored energy? Well, from your formula sheet, you should know that the potential energy of a capacitor is going to be given by this formula right here, which can then also be rewritten as something that looks like this. And well, we know that the capacitance of a capacitor will stay the same as long as the structure of the capacitor does not change, which it does not seem like it is. So doubling the voltage will mean that we're actually going to be multiplying it by 4 right here. And so that means that uh, our new potential energy will be 4 times the original potential energy. And so the answer is E. Number 11, we're given an unfortunately badly printed photo here, but that's okay. We can still basically understand what's going on. We're told that a uniform magnetic field B directed downward parallel to the plane of the page exists in the shaded region shown above, and an electron can enter the field from different directions. So suppose that the electron is moving straight down in the same direction as B when it enters the region of the magnetic field. What is the direction of the magnetic force, if any, on the electron when it first enters the field? Okay, so if we have an electron here entering in the same direction as B, well, it's actually not going to feel any electric or magnetic force. And why is that? Because this is, once again, from the sheet. Uh, this is the magnetic force felt by a charged particle moving. And the key is actually this x right here. This is going to be the cross product. And really what this means is that you'll be doing something that looks like this, where theta here is going to be the angle between the movement of the electron and the magnetic field, or I guess the velocity and the magnetic field, which is to say if they're moving in the same direction, then this is equal to 0, which means sine is equal to 0, which means the whole thing is equal to 0, and so the answer is E. There is no magnetic force. Number 12, we're still working with the same illustration from before, but now we say, suppose that the electron is moving perpendicularly into the page when it enters the region of the magnetic field. What is the direction of the magnetic force, if any, on the electron when it first enters the field region? Okay, so now if we have an electron that's going into the page, that means its velocity kind of looks like, actually no, if it's going into the page, it's going to be with a cross like that. It looks like it's going into it. Well, if we can use the right-hand rule, what you'll see is that your fingers will point to the left, but keep in mind this is a electron, which means it will feel a force that's opposite of the field, or the I guess the right hand rule direction that you came up with. It's going to be the opposite of that, and so the correct answer is actually to the right. For number 13 and 14, we're given here 5 charge distributions, and we're asked in 13, in which configuration is the electric field at P pointed directly towards one of the charges? So let's just think about each one here. In A, there's actually going to be no net electric field. All of them from each charge will cancel out. So it's definitely not A. For B here, well, we're going to have a field that's going like this, a field that's going like this, and by the way, that's from this and this respectively. And then from here, we're going to have a field that's in this direction. Well, the x components on this and this electric vector or electric field vector will cancel out, which is to say that it will all point down into the negative q. And so I already know here that the answer choice is going to be B, the correct one, but you can also try with the others and you'll see that none of them will point to another charge. So correct answer here is B. For number 14, it's still the same charge distribution, but now we're asked in which configuration is the electric potential at P equal to 0. Well, keep in mind that the overall potential will be given by the sums of each individual potential, and each individual potential here is going to be very similar. They have the same radius, all that they differ is in charge. And so we can already kind of make a quick assumption here, a quick guess for how this problem is going to work out, which is that the overall charges need to add up to 0. And you can check yourself why that's going to be true. But from this, the only one that matches that description is going to be E right here. And if you manually calculate the voltage for this, you'll also see that it's 0. But yeah, it's E. Number 15, we're told that the electric potential is 50 volts at point X and 70 volts at point Y, and we're asked what is the minimum average power needed by an external force to move a charge of 4 microcoulombs from rest at X to rest at Y in 5 seconds. And so when you hear about power and you're taking the E&M exam, you might be tempted automatically to try to use this formula here, but it's actually not going to be useful here because we're not given anything that has to do with current, and the other forms here of this formula are also not going to be useful. Instead, you want to use the formula that maybe you learned from mechanics, which is that power is going to be the change or the derivative of work with respect to time. And since we're talking here about an average power, really can just think about work divided by the change in time. Okay, so then what is going to be the work here? Because we know the time, it's going to be 5 seconds. Well, the work, you can know this from your formula sheet, is going to be given by Q times V, where V is just the voltage difference. So you can calculate your work by just taking 4 microcoulombs times the voltage difference of 20. And then when you divide all this by 5, so we're already going to just get the power directly from here, you'll get that the answer that is correct here is going to be E. Number 16, we're told that a small circular loop of conducting wire is near a long straight wire that carries a steady electric current I to the right as shown above. We're asked which of the following actions will result in a clockwise induced electric current in the wire loop. Okay, before even looking at the statements, I would think about what's even happening here. And so first let's think about what the magnetic field that's actually produced at the center of the loop because of this current. And so if it's going to the right, you can use here your right hand rule to figure out that the magnetic field will be pointing out of the page at the center of the loop. And then we need to think, okay, if we're inducing a clockwise current like this, then what's the magnetic field direction that it would be producing inside of the loop? And if you use, again, your right-hand rule, what you'll find is that the induced magnetic field that's inside there is going to be going into the page. So if you think about Lenz's law, but you sort of think backwards here, what this means is that the magnetic flux in the direction that's out of the page must be increasing for us to induce a current that will produce this magnetic field that will decrease the flux. So magnetic flux out of the page is increasing. Okay, so now let's think about each of these statements. Number 1, the wire loop is pulled vertically upward in the plane of the page away from the wire at a constant speed. Well, let's think about that. The magnetic field given or formed by this long current is going to be given by this formula here. And this is not in your formula sheet, but you should either memorize it or at least know how to derive it using Ampere's law. And so you can see that pulling it away will increase R, which will decrease B, which will in turn decrease magnetic flux, given that magnetic flux is given by B dot dA. So it's definitely not 1. What about 2? The current in the straight wire is steadily increasing. Well, if we increase that current, it will increase this, which will increase the magnetic flux, and so that seems to be correct. So 2 is right. And then number 3, the wire loop is rotated about a diameter through a small angle so that it is no longer in the plane of the page. Well, currently it is in the plane of the page, and what this means is that the angle between the normal of the loop and the magnetic field is going to be 0, which means that cosine of theta is going to be 1, which is at its maximum. And so that means that our magnetic flux here, which by the way, this is a dot product, which includes the cosine theta, is at its maximum, given these current values. So if we were to basically pull it out of that angle, it will be decreasing the cosine theta here, which will be decreasing the magnetic flux. And so once again, this is not true. And so the only one that's correct is going to be number 2. So the answer choice that is correct is B. Number 17, we're told that 2 long straight horizontal wires parallel to each other in the plane of the page carry an electric currents to the right, as shown in the figure above, and we're asked what is the direction of the magnetic field at point P midway between the 2 wires. So this question is going to be a combination of the right-hand rule and also knowing that the magnetic field produced by a single long wire is going to be this right here, this formula. And you can either just memorize this or derive this from Ampere's law. But really what's important here is showing that the magnetic field is going to be proportional to I, directly proportional that is. And so now we're ready to answer this question. The bottom current here is going to the right, and so using the right-hand rule, we'll see that the magnetic field at point P will be coming out of the page. Okay, so I'm just going to draw a point right there to the left of that. And now let's think about this top current. And again, if you use the right-hand rule, what you'll get is that you'll have a current that's going down into the page. And I'm actually going to draw this twice because we have double the current, which means we have double the magnitude of B. And so what you'll find is that overall, if these two sort of cancel, you'll still have a magnetic field that's going into the page. And so the answer is D. Number 18 is a kind of difficult question. You have to be good at understanding how magnetic fields look like in space, but we're told that two circular loops of wire, P and Q, are arranged coaxially as shown above, and the current in P is in the direction of the arrowhead. Which of the following is a correct statement? Well, before even looking at these, I would think about what's the magnetic field that this is producing, and so here at P, it's going to be producing in this direction, and same thing as Q, since they kind of look the same, they go in the same direction. Okay, so let's go through each answer trace here. A, if P is moving towards Q, a current induced in Q is in the direction of the arrowhead. Okay, let's think about that. So the magnetic fields produced by P look like this, okay? Which means that we have, well, basically we have the magnetic flux because of P that's actually in the same direction as this arrow here. And as we move P closer to Q, we are going to be increasing that flux in that direction, which means by Lenz's law, we will want to oppose that change in flux. And so we'll want to produce a magnetic field that goes in the opposite direction, which means that actually, no, it will be going in the direction that's opposite of this arrow here. So it's not A. Okay, now let's think about B. If Q is moving towards P, a current is induced in Q, which is in the direction opposite to the arrowhead. Well, this is actually going to be basically the opposite of the previous one, but let's just think about it again. If now we're moving Q closer to P, and by the way, the magnetic flux that's produced through loop Q is still going to be the same as before, which is going in this direction. And if we're moving it closer, then once again, we're making the magnetic flux be stronger towards the left, which means the induced EMF will produce a magnetic field that will be going to the right. And to produce that using the right-hand rule, the direction has to be opposite. And so B is actually going to be correct. But let's think about the other ones as well. C, if the current in P is switched off, a current is induced momentarily in Q in the direction opposite of the arrowhead. Well, if we switch off P, then the magnetic flux that's going in this direction will suddenly decrease, okay, going like that, which means that the induced EMF will actually go in that direction once again, which is, according to the right-hand rule, in the direction that's shown in the arrowhead. So it's not C. D, if Q carries a current in the direction of the arrowhead, the loops repel one another. Well, no, you can sort of think about the perspective maybe along or staring straight down at the loop, which is to say that we have currents that are going in the same direction all around. And if you remember from your unit on magnetic fields, you'll see that actually the force will be attractive for both loops right there. So it's not D either. And then E, if Q carries a current in the direction opposite to the arrowhead, the loops attract one another. Well, no, actually this is sort of the opposite of the previous one as well. But opposite in two different ways, so it actually cancels out and is still incorrect. If the current is going like this, then the magnetic field will be like this, but either way, we have currents that are going in opposite directions, and they actually will repel one another, and so E is incorrect as well. So the answer choice here that is correct is going to be B. Number 19, we're given a circuit shown above, and we're asked immediately after the switch is closed, the current in the 3 ohm resistor is most nearly. Well, at times equal to 0, the voltage across, well, actually really the charge of a capacitor is going to be 0, which then is why the voltage is going to be 0 as well. So if there's no voltage across here, we can sort of think about nothing. We can just sort of imagine that the capacitor doesn't exist there. And so all we're left with is here two resistors that are in parallel with each other. And so using this formula here, for parallel resistors to find the equivalent resistance, what we'd get is that the equivalence resistance is going to be 3 ohms. And then adding that in series with this tells us that the overall equivalent resistance is actually going to be 6 ohms. And then using the formula that I is equal to V over R, or just using Kirchhoff's rule, you'll see that the current is going to be 1 amp. E. Number 20, we're still working with the same circuit from before, but now it's a long time after the switch is closed, and we're asked what the current in the 3 ohm resistor is. So as t approaches infinity, the current through the capacitor is going to be 0. And since the capacitor and the 6 ohm resistor are in series, then that means that the current through the, this is going to be kind of difficult, but the second 6 ohm resistor is also going to be 0. So basically, no current is going through here, and we can just really think about the current in this direction here. And so then the overall equivalent resistance of that is going to be 3 ohms plus 6 ohms, which is going to be 9 ohms. And then using this formula right here, once again, or just Kirchhoff's rule, you'll get that I is going to be equal to 2/3 amps, and so that's going to be 0.67. That's D. Number 21, we're told that a negatively charged particle initially in region 1, as shown above, is accelerated from rest by an electric field of magnitude E between two parallel plates separated by distance D. The particle then enters region 2, the space between two parallel plates with a separation 2D and an electric field of magnitude 3E in the opposite direction. How far into region 2 does the particle travel before reversing direction? Okay, so this is actually going to be a conservation of energy problem, maybe a little bit like you'd expect to find in mechanics. And so let's write out here the formula, which is very, very important. And let's think about what the initial state and the final state look like. So initially, we are at rest, which means velocity was 0, which means kinetic energy is 0. But then what about our initial potential energy? Well, we can think of our initial potential energy as Q times V, right? And we know this from our formula sheet. But what is actually V? We're not told explicitly what V is in this problem. So we need to instead use this formula here, which we get from just rearranging this formula that's in your formula sheet. And so here we have a electric field that's called E0, and we have a distance of D. Okay, so, oh, whoops, sorry, that should be like that. Okay, now let's find the other part. The final state is going to be when we finally reverse direction, which if you remember from kinetics, from kinematics in mechanics, had to do basically when velocity was going to be 0 again because we're reversing direction. And you also know this from calculus, which is to say that the kinetic energy at the final state is still going to be 0 because, again, velocity is 0. So then we're just left with a potential energy. And what is this potential energy? Once again, it's going to be Q times V. But what is this new V? Well, let's think about what's really happening is that the charge is going out to some distance here. Let's call it x. And then it's basically going to reverse direction right there. But the voltage from here to here, given that we have a constant electric field, well, the voltage is just going to be 3E0 times x. So we can write Q times 3E0 times x. Okay, now we can just solve for x, where we cross out the q's, we cross out the e0s, and we're left with d is equal to 3x, which is to say that x is equal to d over 3, and ta-da! The answer choice is A, that's correct. And if you just think about it, that sort of makes sense. We are increasing here the magnetic or the electric field by strength of 3, and so it makes sense that then the distance is going to be a third of that. Number 22 was the second most missed question on this exam. So let's be careful here. We're told that a student wants to construct an inductor of a given inductance using copper wire and a plastic tube. If a sufficient supply of copper wire is available, then the student will also need A, and then we're given a bunch of materials and we're thinking, what the heck is going on here? So what we might do is think about our formula sheet, and one of the formulas that will come to mind is this right here, which is given to you. And you might think, well, let's just solve for L, because keep in mind, the student wants to construct an inductor of a given inductance. That's basically the important part here. So we might think, okay, well, then let's just say that L is going to be negative EMF over di dt. And then once we see this, we might start looking at these answers here, because they include a voltmeter and we're thinking voltages, but actually we're going in the wrong direction. Why is that? It's because inductance here, L, is just a property of the material or of the object that you're dealing with. It's not actually dependent on voltage. It's similar to how resistance, for example, you can have this formula here, and then you can say that, well, R is going to be V over I, but that doesn't mean that changing the voltage will change the resistance of a resistor. The resistor is actually given by another formula. The resistance of it is given by this formula, which is dependent on the structure itself of the material. The same thing can also be thought of for C, which is capacitance. You might know this formula here, or you should know it, but you also will know this formula right here, which actually gives you the real capacitance based on the structure of the capacitor. So then you might be thinking, okay, then what's the equivalent thing for a inductor? And well, it's not given to you on the exam on the formula sheet, and so it might be more difficult. But there is this formula that maybe you got from your textbook, which goes like this, where N is basically the number of turns in a coil, which we can imagine is what's happening here because we have an inductor, or we have a copper wire and a plastic tube. We can imagine that the copper wire is going to wrap around the plastic tube and create a solenoid of sorts. But the formula here for L is going to be big N, which is the number of turns, times the magnetic flux through each of those turns, divided by I here. Okay, so what we just need to understand here is that it's dependent on the magnetic flux, which has to do with basically the area that it produces as it wraps around. And since we know the plastic tube, we can measure its radius, we can figure out what that area is going to be, which means all we actually ever need in this is going to be a meter stick. As long as we have a meter stick, we can figure out what the inductance is going to be as we measure the radius of the plastic tube, but also the distance of the copper or the length of it that we can wrap around to figure out what N is as well. Also, I should mention the reason we don't have to care about the current right here is because the magnetic flux is given by this formula here, right? B dot dA. Uh, and so the B and the I are basically going to cancel out because keep in mind the current is going to produce a magnetic field. So we really don't have to be thinking about this. We just need to be thinking about the area portion of the magnetic flux. Number 23 is also a tricky problem. We're told that the correct statements about a constant magnetic field acting on a charged particle include which of the following, and then we're given three statements. Let's think about it. So, one, the field can accelerate the particle. Well, that's true because a magnetic field can definitely create a magnetic force, right? And we know that a net force is also the same thing as acceleration. Now, we need to be careful here because a magnetic force, if we have a particle that's moving in this direction here, for example, then we could have a magnetic force that's perpendicular to it. And what this does is it's not going to actually change the speed right here. It's just going to change the direction. This is what we call a centripetal force because it will always be acting perpendicular to the speed or velocity of the particle. But one is correct. Two, the field can change the kinetic energy of the particle. Well, no, because I just said that we can't actually change the speed of this particle here. We can only change the direction. And so since this is kinetic energy is given by this formula right here, being unable to change the velocity means that we cannot change the kinetic energy. So 2 is not correct. And then number 3, the field can do positive work on the particle, where you can think of work as the change in kinetic energy, and we just said we can't change the kinetic energy. So we can also not do any work. So 3 is wrong, and so the only one that's correct is 1, which is A. Number 24, we're told that a metal wire has a resistance R when it is at a temperature T. The wire is melted and all of the metal is used to reform into a new wire 4 times as long. What is the resistance of the new wire at temperature T? When you first read this question, you might be scared because we're talking about temperatures and you're thinking, this isn't AP Chem, why are we talking about temperatures? Well, that just has to do with the fact that the resistance can depend on the temperature. But here, the temperature does not change, so we don't have to worry about any of that. I don't believe it's even in the curriculum. So let's just think about what's really happening here. We're taking a metal wire that has a resistance R, and then we melt it, and then we reform it, but now the wire is going to be 4 times as long, but we're still using the same volume of metal. And we're just thinking about what's going to be the new resistance. Well, let's just first write the original resistance, which is going to be given by this formula here. P here, or really it's called rho, is going to be the resistivity of the material, and since the material does not change, this does not change either. But the length, let's just call it originally L, and the area A is just going to be, well, the area of the wire, which is also, in other words, going to be given by this formula right here. So then what happens when we melt it and reform it? Well, we're keeping the volume the same, which means originally the volume of metal that we had could be given by L times A, right? Uh, but what we're going to do is we're going to reform that where L is now 4 times as long, so like that. But then that must mean that the area must be a fourth as big, right? Because we need to keep the same volume. So by quadrupling the length, we're going to be cutting the area in, well, I guess in 4. So we can now rewrite this with the new resistance, okay, which is going to be still the same rho, but now we have 4L over 1/4 of A. And so if we rearrange this, that means that R2 is going to be rho times 16L over A, which is really just 16 times the original one that we had up here. So the correct answer is E. 25, we're told that an isolated hollow conducting sphere carries a total positive charge Q, and then we're asked about correct statements from these three here. Okay, so that will basically look like this. Let's just draw something that looks like that. And using Gauss's law here, we can draw a Gaussian surface that will enclose the sphere. And what we'll see is that the electric field definitely is positive. It will be sort of going out like that. That arrow up there is a little bit crooked. Let me try to fix that. And it's going to be going out radially outward because we can sort of think of anything that's spherically symmetric as really just a point charge, and we know that point charges give off radially or radial electric fields. So one is going to be correct because of that, and it is coming from outward from the surface of the sphere. Number two, the electric field is zero outside of the sphere. Well, no, we just calculated here. Using Gauss's law, we can definitely prove that since there's a charge that's enclosed, that it's not going to be zero. But is it going to be zero inside of the sphere? Well, we can use the same logic here, which is that a Gaussian surface will have no enclosed charge inside, which means that the electric field would be zero. But also we can just think about the fact that it's a conductor. Okay, it's a conductor, which means that all the charges will be spread evenly. And normally we have no electric field. Well, actually, we never have an electric field inside of a conductor. But also the fact that it's hollow means that there's nothing inside of it, and so there's not going to be any other like electric field that could be produced inside as well. So we could sort of come at it from two different perspectives. But either way, we're going to get that 1 and 3 are correct, and so D is the right choice. Number 26, we're told that the diagram above shows the electric field lines due to two charged parallel metal plates, and then we are given 3 points here, x, y, and z, about potential locations that we can place a charge. So which of the following must be true? Let's go through each one. A, the left plate is positive and the right plate is negative. Well, electric fields go from higher potential to lower potential, which means that really what's going on is we're uh, negative on the left and positive on the right, so no, it's the opposite of A. B, a negative charge at X experiences a greater force than it is if it was placed at Y. Well, force is going to be given by Q times E, like this, where E is the electric field. And the fact that all these lines here are first parallel, but also they are equal in density, as you can see here, they are evenly spaced out. That tells us that the electric field magnitude is going to be the same throughout this entire region here, okay? So the electric field is, the magnitude of it is going to be the exact same. Also, the direction is going to be the exact same throughout the entire region here. And so actually we can look ahead here and B is going to be incorrect, C is going to be incorrect, and D is going to be incorrect because it's all saying something about different amount of force, but it just is not true because the electric field stays the same. So then we're left with E here, which says a positive charge at X would experience the same force if it were placed at charge Z. It's true, we have the same charge, so the Q stays the same. The electric field, like we've been saying, is the same throughout the entire region here, so E is correct. Number 27, we're told that when two metal objects X and Y are connected to each other by a conducting wire, object X gains electrons. Okay, so let's see here. We have X and then we have here Y, and they're connected, and electrons seem to be going from Y to X, right? That's the only way that they can be moving, or that's the only way that X can be gaining electrons, that they're moving out of Y. From this information, it can be inferred from before the connection was made, object X compared to object Y must have had. And this is actually a question where I think it's easier to just get to the right answer and then, hope that it's in our answer key or in our answer choices than to try to eliminate each one. I think you'd spend too much time thinking about it. So if electrons are moving from Y to X, well, we know that negative charges like to move from areas of negative voltage to areas of positive voltage. So we have a negative voltage here and a positive voltage here. By the way, an electron is going to be doing the opposite of a positive charge, which would be going from positive to negative voltage. Uh, and really, that's all I need to know here because we're already given here an answer choice that makes sense, that X is going to have a greater electric potential, which is true. All the other ones, you can sort of spend some time thinking about it. They don't really make sense. All that really matters is here the voltage to determining where the electrons will be moving, since it's all metals that are connected. Number 28, we're told that two long straight current carrying wires are parallel to each other in the plane of the page and separated by distance A as shown above. The direction of the current I in each wire is toward the top of the page. Which of the following best represents the force per unit length acting on the wires? Okay, so first, I would recommend that you memorize the fact that currents moving in the same direction will have attractive forces. So the forces will be experienced like that. You can derive this, if you forget, by just using the right-hand rule, and you have to use it twice basically because you're creating a magnetic field. This is creating a magnetic field here, and then you have to think about how that magnetic field is going to create a force on this, and what you'll find is that it's attractive. So we can already eliminate A and B. Okay, but let's actually think about the magnitudes of these forces. Well, the magnetic field, let's just think about this here, creating a magnetic field right there, is going to be given by this formula right here. Well, A here because we're plugging it in for R. Normally we'd have R here. And we can derive this from Ampere's law, or I would recommend also to just memorize this for the exam. Okay, and so with this, now we need to also think about, given that there's a magnetic field right here, on this area right here, what's going to be the force experienced by I? And so that's another formula. That's a formula that's actually given in your formula sheet, which is going to look something like this. And it looks a little bit more complicated than it really is. All that really is saying, at least here we can assume because the magnetic field and the current are perpendicular, and also it's the same current and same magnetic field throughout, we can just say I times L times B. Well, we want to know the force per unit length, which is really just saying FB divided by L. And then we can plug in the B here that we got from up here to get something that looks like this. And so we can see here that the correct choice will be C. Number 29 was the most missed question on this exam, which surprises me a little bit because it's really actually quite simple as long as you spot uh, the key word here. And so let's just get to the problem. A negatively charged rod is brought near a metal object on an insulating stand as shown above. When charges stop moving, the left side of the object has an excess positive charge, and the right side of the object, where the radius of the curvature is less, has an excess of negative charge. Which of the following best describes the electric potential on the metal object? Okay, look, you actually don't even need any of this. All that matters is this last statement. Which of the following describes the electric potential on a metal object? A metal object is a conductor. The electric field inside of any conductor is going to be zero throughout the entire thing. And given that V is equal to E times D, that tells me that the voltage will be the exact same throughout the entire object, which tells me that D is correct. Okay, but again, why is this true, and why are all these shenanigans being told about a negative rod? It's there just to trick you. All they have to care about is that a conductor will have an electric field of zero, and so the voltage is the same throughout. Please just memorize this fact. It will get you so many points and also save you a lot of time. But let's just think about it a little bit, in case this is kind of weird to you. This is the most missed question, so maybe you missed it as well. If the charges stop moving, and given that we have a conductor, which means that electrons are free to move around, then that means that the electrons have gone to their lowest potential energy, right? Because if there was a potential energy, a spot along here, which really means that there's a voltage, a positive voltage, given that electrons like to go to areas of positive voltage, if there's some area along here that is more favorable for the electrons to go to, they will go to it because it is a conductor. They are free to move around until they stop moving. And they'll stop moving once they reach that optimal potential energy setup. Given that they stop moving, we can assume that it has reached that point, which means that there is no potential difference inside of here, or else the electrons would move to it. Okay, so that is why the answer choice that's correct here is going to be D. Please just memorize that conductors have an electric field of zero, and their potential is the same all throughout. Number 30, we are given here a charge distribution that is tetrahedral, and we are asked about the electrical potential energy of this arrangement of charges. So electrical potential energy, that looks like this. That's equal to just QV. So really all we care about here is the V, and we just have to remember to plug in the Q back in at the end. But the V is going to be the difficult one. But since we have here a bunch of point charges, we can really just do the sum of all the voltages from each point charge as it takes each charge to be put in place. So we need to start thinking about, okay, let's just name this 1, 2, 3, and 4. The first voltage is just going to be 0. And why is that? Because there is a voltage of 0 when there are no charges here. Bringing in the first charge is traversing no voltage difference, basically. So the first voltage is just 0. The second voltage, well, now we have a charge right here, and we're bringing this one here out from infinity to this place. That's going to just be a voltage of, well, we can use here the point charge formula for voltage, which is going to look like this. And actually, let me just use K because we're going to be writing a lot of these. And it's going to be Q over L, where L is this distance right here. Okay, and so that's voltage 2. Voltage 3, to bring in the third, now we have these two charges, and let's say we're bringing down this one here from infinity. Well, it's still summing up the voltages, and so we'd be adding Q over L because it's the distance from here to here, and it's this Q that we care about, and then plus another QL, which is to say we really just have 2QL because, by the way, the distance here is also the same. Okay, cool, we have voltage 3. Now voltage 4 is not going to be a lot different. It's just now we're bringing this one here in, but now we have 3 voltages from 3 different charges here, and they're all the same, which is 3QL. And so summing all this is going to give us K times 6Q over L. And then let's just remember that we are actually going to be talking about the potential energy uh, arrangement of this, which means that we're just adding another Q here, um, because that's we have to add here basically. We're talking about the potential energy that it takes to bring in, or the potential energy for bringing in that last charge, which means we multiply the whole thing, this voltage here, by Q. So sorry for that long explanation there, but we should get something that looks like this, and so the correct answer here is E. Number 31, it's still the same charge distribution from the previous question. We're asked one of the 4 charged particles is released and allowed to move away under the influence of the electrostatic force from the other 3 charges. How much kinetic energy will it have when it is very far away? Well, when it's very far away, we can reasonably assume that the voltage difference, or really the potential energy, is going to be just 0, which means that all of the initial potential energy became kinetic energy. Okay? So, actually, I could just say equals right there. So, what is the initial potential energy? Well, we can actually just cheat from our previous work up here, which is that the initial potential energy is just going to be given by QV, where V is going to be the arrangement of the of these right here. What's the voltage on, let's just say this one here is the one that we're going to be moving out. Well, we've actually already know that that's going to be V3, which we got from up here. Or actually, sorry, it's going to be V4. It's the fourth one. Sorry, I'm sliding all around here to just cheat off my previous work, which is to say that this is just going to be K times 3Q over L. Um, and keep in mind that we then multiply by Q, where Q here is actually going to be big Q because that's the charge right here. So let's just square this, and what we have is C as the right answer. And so unfortunately, you kind of need to get the previous one correct to have a good shot at getting this one correct as well. Number 32, we're told that the circular wire loop shown above has a resistance of 30 ohms and an area of 3 meters squared, and it is fixed in position in the plane of the page. A uniform magnetic field B is directed perpendicularly into the plane of the page, and we're asked the constant rate at which the magnetic field would have to change in order to induce a current of 1 milliamps in this loop is most nearly. So really this is just a Faraday's law problem, but we kind of are working backwards a little bit. So we know that current is given by EMF over R, but then we know that EMF is given by the change in magnetic flux over time. Uh, we know that magnetic flux is given by B dot dA, which for all intents and purposes here, everything kind of works out nicely. We just get BA, which is then to say, since the area does not change with time, but what we're asked about B changing with time, that means that the EMF is going to be given by the change in magnetic field over time times A. And so putting all this together means that current is going to be given by dB over dt times A over R. And now keep in mind we're asked to solve for the constant rate of which the magnetic field changes. And so that means that we're solving for this right here. And what you'll get is that the dB over dt is going to be given by IR over A, and we can just now plug in current is going to be 1 milliamps, resistance is going to be 30 ohms, and area is going to be 3 meters squared, and what you'll get is that the magnetic field must be changing at a rate of 1.0 times 10 to the negative 2 teslas per second, so the correct answer is D. Number 33 was also a pretty highly missed question, so let's once again be careful with it. we're told that two identical capacitors, X and Y, are connected in series across a battery. So let's just say it looks like this, and they're identical capacitors, so their capacitances are the same. And then we're told that a dielectric material with K being equal to 5, the K constant here, being placed on capacitor X. Once equilibrium is reached, how do the potential differences across the two capacitors and their charges compare? Okay, so let me draw here two, and one of them will have the dielectric constant in it, but it's still going to be called X right there, and this is going to be called Y, and it's still the same potential difference, okay? So we have here some potential difference, some potential difference. Okay, so how do these change? Well, first thing to think about, and what you need to understand 100% is that when a dielectric material is added, what it first changes is the capacitance, okay? And we know this because the formula for capacitance is given by this fraction here, and so this is actually where the k comes in, is right there. By basically, normally the k is equal to 1 when we don't have a dielectric, but now if we're increasing it to 5, that means we're also increasing the capacitance. So that means that the capacitance is increasing, which means that, and it's increasing by a factor of 5, by the way. So we have here a 5C capacitance. Let's just say here we have C, and here we have C for both. Okay, so now we need to also think about what's going to stay fixed and what's going to change in this problem. Can the voltage across X and the voltage across Y differ? Yes, they can. Okay, yes, they can. Especially when it's in series, it can. When it's in parallel like this, it cannot, right? Because the voltage difference across here must be the same as that voltage difference, right? So the voltages can change, but the charges cannot, okay? And so the charges that are on this plate must be equal to the charges that are on this plate. And if you need to have a better understanding of that, I would recommend rereading your textbook page when they were first introducing capacitors in series, and it'll explain that in a little bit better detail. But to me, that's actually really useful to me because I can eliminate all the answer choices where the Q's are different. Because these are in series, I know that the charges must be the same. So at least now we're down to B and D. And now we're just left to think about the voltages. Well, I know that C is equal to Q over V, which means that V is equal to Q over C. And in this X capacitor, what's basically happening as I go from here to here, keep in mind, originally they have the same voltage as well, X and Y, because they have the same capacitance, they have the same charge, they're identical. But as I go from X and I put in the dielectric constant, I'm increasing the capacitance, right? Because I'm changing the actual uh, physical properties of the capacitor, which means I'm going to be decreasing the voltage. And then by comparison, because the voltages must stay the same across the entire thing, because they have the same battery hooked up, then that must mean that Vx is going to be less now than Vy, and so the correct answer is going to be D. Number 34, we're told that a small sphere of mass m and charge q is constrained to move vertically in an insulating cylinder, as shown above. At the bottom of the cylinder is a point charge plus q. At what height h above the bottom of the cylinder will the small sphere of mass m be in equilibrium? And so this is a little bit like a mechanics question. We have a plus q charge here that will be feeling definitely a gravitational force down. And the reason you know there's definitely going to be this force is that whenever they mention the mass, that usually has to do with the gravitational force. Yeah, it almost always is like that. But it will also be feeling a electric force upwards, and you can know that because we have here a point charge that's positive. That means the electric fields are going up. Well, they're going radially, but for what matters here, they're going up, which means right here it's going up. And since we have a positive charge, that means it's going to go, the electric force is in the same direction as the electric field vector. So if it's going to be an equilibrium here, um, then that must mean that f of E is equal to f of G, which is to say that Q times the electric field E is going to be equal to mg. And then this electric field vector is going to be given by K times big Q here, because it's being produced by this charge right here, over R squared, right? Well, R squared is actually just going to be H squared, because this distance here is exactly what they're asking us about. So we just have that now. So we can then replug this back in. We say that it will look something like this formula here. That's equal to mg. And keep in mind, this is a force. This is not potential energy because of gravity, so don't include an h right there. And now all that's left is solving for h, and so we get something that will look like this. And then we're just taking the square root, which means the answer choice that's correct is going to be E. Number 35, the final question, is a little bit similar to the previous one in that it requires you to think like a mechanics student a little bit when it comes to torque, at least, because we're told that a square wire loop of side D carrying current Y is in a uniform magnetic field of magnitude B in the position shown above. There is torque on the loop. The magnitude of this torque is going to be what exactly? Well, torque from your mechanics is going to be given by this formula right here, where it's F cross R, but really we just care about the magnitude, so we could just think of it as F times R, and we know the magnitude is going to be, well, the cross product will just be the cosine of 1, or sorry, cosine of 0, which is 1. So we have here F times R, where R is going to be the distance from the axis of revolution here, of rotation, I should say. But F here is going to be the magnetic force that's imposed on this wire by the magnetic field. And keep in mind that the magnetic field here is going to be, or the magnetic force onto a wire is going to be given by this formula from your answer sheet, or from your formula sheet. I'm sort of at the end here. I keep slurring over my words. This can be simplified to be ILB because we are perpendicular, and also the current is the same, and the magnetic field is also the same. So we can just say I times L times B. But what are each of these points right here? Well, first we need to actually keep in mind that this is not applying to this or this, because those currents are going parallel to the magnetic field, so there actually the cross product would end up being 0. So we're just thinking about this and this. Okay, and the magnetic force is going to be given then by I times L, where L really is going to be 2D right there, because we have a length here of D and another length of D here, and I'm just going to sum them now, which means we have something that looks like this, and then we have a field B right there. But then plugging this back into our formula for torque, keep in mind that R really is going to be based on the axis of revolution, which is right there. And so R here in this case is going to be D divided by 2, which is to say that the magnitude of torque is going to be given by 2IB times D squared over 2, which is to say that the magnitude of torque is going to be directly proportional to D squared. So the correct answer choice is B. And congratulations, you've made it to the end. Hopefully you did well. If you want to actually know, I was able to find a scoring statistic here, and the average student that got a 5 on this exam was able to get 26 multiple choice questions correct. Okay, so that's the average student getting a 5. So you could get a little bit lower and still get a 5, or at least be in the range of a 5 for this question here, or for this exam. But so just keep that in mind. If you're scoring above a 26 and well above, then you're definitely going to get a 5, I would hope, on the actual exam. Uh, but hopefully you found this video helpful and educational. I will try to get the answers to the 2012 multiple choice before May 3rd, but also I'm a busy person and I have to study for the exam on my own time as well, because making these videos helps definitely a little bit, but I also want to be studying my own things as well. But hopefully I'll try to get that out to you, and hopefully it'll be really helpful. But thank you so much for watching. Please like the video if you enjoyed it, and also subscribe if you want to see more content like this, and let me know what videos I should make in the future.